Welcome to Integrated Math 3. On this episode, Stevenson will demonstrate
what I want to show you is some techniques that can be used to help you when your rational functions become a little more complex. And I like to just refer to them in general terms as end behavior asymptotes. So we're going to go beyond this idea of horizontal asymptotes and using transformations to find them. So what I'm going to show you is how you can find horizontal asymptotes with minimal work. I'm going to show you how you find, or at least tell you how you find oblique asymptotes, what they are, and I'm going to tell you how you can find x-intercepts. Lastly, we're going to use all of our knowledge to actually come up with sketches. I'm going to go over the procedures, and then hopefully I'll have enough time to show you at least one example. So here's what we need to know. An end behavior asymptote is basically an asymptote that we use to describe what happens at the ends of our functions, how they behave. It is possible for the graph to cross an end behavior asymptote depending on what it is, okay? And the beauty of this and what I'm going to show you is that you can actually figure out the end behavior asymptotes without much work at all, especially when the rational functions become more complicated. And essentially what we're going to look at is what happens when your rational functions, the numerator isn't a constant. They behave very differently. So in general, what I want you to kind of start thinking about is that there's two types of end behavior asymptotes for a rational function. They can be horizontal, which is what we've been dealing with, or they can be what's called oblique. Oblique is just some fancy way of saying not horizontal. So think of like diagonal, for example. So look at these three graphs. Take a moment, pop them into Desmos. What do you notice about how they look? But more importantly, what do you notice about the degrees in terms of the numerator and the denominator? Look at each one of them. What do you notice? Did you notice that they all have a horizontal asymptote of 0? Okay? The numerator also will give you the x-intercept after the function is simplified. Okay, so what does it mean to simplify? Well, if you factor the denominator, if something simplifies with the numerator, what's left over will give you the x-intercept. So that's very handy. So what does this mean in general? In general, if you have a rational function, so this is a fancy way of showing a rational function. The numerator is some polynomial where its degree is n, and the denominator is another polynomial where its degree is m. So these other terms right here just show the remaining terms below those. So just ignore those for a moment. If we look at just the leading terms, just them, the a and the b, the coefficients, we can actually find our end behavior asymptotes. It's pretty cool. So if you look at the degree of the leading term for the numerator and the denominator, if the degree in the numerator is smaller or less than the degree in the denominator, then your end behavior asymptote will automatically be horizontal. In other words, y equals 0. Now, this refers to any rational function that is not a transformation of the parent rational function. Please make that clear in your notes. Also, after you simplify your rational function, if you set your numerator equal to 0 and solve, those solutions you get will represent any x-intercepts on your rational function. It's pretty cool. Let's look at another scenario. Here are 4 different rational function graphs. Go ahead and pop these into Desmos. And again, make a mental note of the degrees of the numerator and denominator. And then look, what do you notice about the graph and how it's behaving? What do you notice about its x-intercepts? What do you notice about its end behavior? Well, did you notice that all of the horizontal asymptotes are some value, but more importantly, it's a quotient of the leading coefficients. Check this out. This is so cool. So if the degrees are the same, so look at k of x. Look at your graph of k of x. They both have the same degree at the top and the bottom. You see that? Their end behavior asymptote was y equals 1. That's if you just take the numerator 1 divided by 1 here, and the denominator's coefficients. Look at g of x. You see how their degrees are both 2? Well, if you take 2 divided by 1, you get an end behavior asymptote of 2. Look at h. The degrees are the same, 2 over 2. So then it's just 1 over 1 for your end behavior. Lastly, in f of x, again, the degrees are 2. So you do negative 3 divided by 1. So your end behavior asymptote is the horizontal line y equals negative 3. So you don't have to do any work. So let's review. Again, you look at the leading terms, okay, the highest degrees. You look at their coefficients. So we already know if the degree in the numerator is less than the degree in the denominator, then the end behavior is a horizontal asymptote y equals 0, also known as the x-axis, right? However, the new part, if the degrees are equal, then the horizontal asymptote is the quotient of the coefficients. Whatever those numbers are, you just divide them. So easy. Please remember though that the x-intercepts are still the numerator, but after you simplify it, you set the numerator equal to 0 and simplify. We have one more scenario. So far we've looked at when the degrees are the same, and we've also looked at when the degree is bigger in the denominator instead of the numerator. So the last situation is, well, what if the degree in the numerator is bigger than the degree in the denominator? So I gave you 5 functions to look at. These things look super weird. What I also gave you though is the bounds in which the viewing windows in which you want to view them at. So go take a moment, graph these, and just look at them. These things are crazy looking. In this case, every single one of these end behavior asymptotes are not horizontal, they're oblique. So they are some other function. They might be linear, they might be quadratic or cubic. It's just weird stuff, man. So how do you find it? You have to use long or synthetic division to figure out what the actual end behavior asymptote is. Don't stress, we're not going to actually do it. We don't need to do it at this level. So let's sum up everything we've learned. If the degrees are the same, so again, we look at the leading terms, we look at the degree and the leading terms there. If the degrees and the numerator is less than the degree in the denominator, the end behavior asymptote is just y equals 0. If the degrees are the same, then the end behavior asymptote is whatever those two numbers in front are divided. But if the degree in the numerator is larger than the degree in the denominator, then the end behavior is what we call oblique. In other words, it's not horizontal, and we have to use long or synthetic division to figure out what it is. Lastly, after you simplify your rational function, take the numerator, set it equal to 0, and solve to get your x-intercepts.